Exercise 1676, page 444, question 2, part A. d by dx of this function here involving t, so I have to differentiate with respect to t, 5 over 2 log 3t, and then multiply that by dt by dx, which is a variable I want. Looking at the table of standard differentials, I can find out what the differential of the log of 3t is, and then surely come up with the answer in the textbook. Part B, a little more involved, because in here I have a e to the 2y plus 1, and if you remember back to the use of the chain rule, that's how we would do something like that. We've got one function inside another. We've got 2y plus 1, and then the whole lot, e to the power of that. So I've got to use the chain rule in this, as well as the idea of these implicit differentials. So what do we do? Equals, well, first of all, d by dy of this function, 3/4 e to the 2y plus 1, but multiplied by dy by dx, which is what we want. So this equals, I would suggest we take the 3/4 outside of this square bracket just for the time being. So 3/4 times d by dy of this e to the 2y plus 1 multiplied by dy by dx. Now we have to use the chain rule for this part. So we let u equal 2y plus 1, which means that du by dx, or du by dy rather, equals 2. And then we say that d by dy of this function, e to the u, equals d by du of e to the u multiplied by du by dy, using the chain rule. Well, the differential of e to the u with respect to u is just e to the u, and we've worked out what du by dy is. It's 2 times 2. So the differential with respect to y of e to the u is 2e to the u. So therefore we can write, going back to our implicit differential, this equals 3/4 of 2e to the u times dy by dx. Tidying up, 3 times 2 is 6 over 4. E to the u, and u is 3x plus 1, or sorry, 3y plus 1, isn't it? Yeah, 2y plus 1. Times dy by dx. I can tidy that up a step further. 3 over 2 e to the 2y plus 1 times dy by dx. So that's not a straightforward solution. If you look though at this part of it here, is e to the 2y plus 1. We talked about this idea of the chain rule before in words. How do I find the differential of this? It's the differential of the function with respect to the bit we're going to call u, and then multiplied by the differential of the part we've called u. So if you look at this, we could have written down the answer, because what's the differential of e to the 2y plus 1, ignoring the 2y plus 1 part, just e to the 2y plus 1, which is in our answer, here, but then we multiply that by the differential of the 2y plus 1 bit, which is just 2. So we multiply that by 2, in other words, here. Not straightforward, but it's there, so have a look at it. Check you understand it. Part C, this one involves another standard differential that we haven't really talked about in detail yet. And if you look in this folder on the chapter on implicit functions, you'll see an extended table of differentials. And here it is. Oops, wrong one. Where is it? So I'll put it in this table of this folder of implicit functions, and it is introduction, extended. Here we go. Extended table. If you look at this table of differentials, at the bottom here, you've got 2 extra ones, and how they're arrived at is laid out on page 419 of the textbook if you want to have a look. But once they've been worked out, we can just add them to our table of differentials. The differential of tangent of ax is a sec squared ax, and the differential of sec ax is a sec ax tan ax. So you might want to add those to your table, and we're going to use this to do our complete this problem. So we've got the tangent function. So what do? Differentiate with respect to y to tangent 3y and multiply that by dy by dx. And then we look at our table of standard differentials, and we note that the tangent is the a comes out and the tangent changes to sec squared. So the a comes out, the tangent changes to sec squared. So this will equal 3 comes out times by the 2 to get 6 sec squared 3y times dy by dx, which is the answer in the textbook.